Hey, Diane, thank you. We're going to transition over to Ram Narayanamurthy. He is the technical executive at the Electric Power Research Institute, which is an international organization that services utilities. And he's going to talk about our sort of future grid. And it's a very nice transition from Diane, who's showing us what is the biggest grid impact, which is going to be electrifying our transportation system. That's going to be massive. And building electrification goes with that. So Ram, are you there? We're doing the checking. Let's see, I'm gonna unmute you. Let's try that again. Ram, can you say something?
Yeah, can you hear me?
Now we can.
Sean?
Yes, perfect.
Okay,
So,
great, thank you.
So I'm gonna hand it over to you. You just tell us next slide when you're ready, and now this is your show. Go for it, my friend.
Okay, thank you. Hey, Sean, so just one thing, my Zoom just dropped out about a minute ago, but I have my slide deck up, so I'll just keep moving it, okay?
That's perfect.
But I'm going to try to get back on Zoom. Give me about 30 seconds.
No worries. We can just keep on moving with it.
Yeah. Okay, so thank you again, Sean. Thanks for the opportunity, and it's been very exciting and interesting just listening to the presentation. So I think as we start getting to this new age where we are right now on the cusp of a pretty big transition. Are you on the first slide, Sean?
Yes,
one with the.
We're on the first.
Okay,
slide.
perfect.
You say next.
Okay. So I just wanted to kind of raise this question of like, has anybody seen this curve? It looks familiar, but again, it's not totally familiar. And the reason is, if you click on, it looks like the famous duck curve that we talk about in California, but it turns out that this is a curve from actually from Italy. And it turns out the Italians actually ran into the similar issues about 3, 4, 5 years ago, and it's getting deeper and deeper. So what we are facing today is not something that's unique, but it's actually a lot of different areas in the world are actually running to it right now. If you get to the next slide, just one second. Sean, if you can hold on for 1 second, I'm just trying to join in.
I understand. What we're seeing right now is your next slide where you've
Yeah.
got the colored graphs on the left and blue graph.
Right.
Right. Net load per 1 week.
Okay. So what that shows is actually two other grids, right? One is actually the ERCOT grid, and you can see what's happening in the ERCOT grid is that there's a lot of variation. This is actually a windy day, and with wind, you get a lot of variation, a lot more than you get with solar, right? So on the same day, you could have over generation, under generation, and then huge swings in power production just within like a 15-minute period. So what that means is that you need loads that can be changing quite fast. You also need other types of storage. Maybe it's battery storage. Maybe it's backup power. Whatever it is, right? You have to have a lot of different resources that vary really fast to be able to manage the grid. And then on the right, what you see is actually a weekly load profile for a Z&E home in California. And what it shows is that the typical duck curve, or the typical curve that you see with these kinds of load profiles is not just limited to the bulk grid, it's actually even at the local grid level. So when this happens, so what this means is that there's various parts of the grid and the electrical system where you see these problems happening. And so what this means is that as we grow clean generation, as we decarbonize, what we need also is flexible buildings. But flexibility, what we really have to look into is when, where, and how. We are still trying to find out where that when, where, and how happens. If you go to the next slide. So this next slide is essentially a quick synopsis of all the different areas where we need flexibility. When we talk about the goals that we have for renewables, when we talk about achieving carbon-free electricity. What we're talking about is the energy from the bulk grid. And that energy is over any period of time, usually annual or over some fixed period of time. But what that doesn't tell you is what happens to the capacity in both the bulk grid and in the distribution system. And what that means is that as we get more renewables in the system, what you see with the duck curve, for example, is a issue with the bulk grid capacity. You have a lot of excess capacity during the middle of the day as you get more utility solar into the grid, and then you end up with these evening ramps and peaks. Now, what happens with the distribution system is actually quite different in that the distribution system is essentially serving your loads, whether it's EVs, whether it's electrification of end loads, but it's serving your loads. And the challenges as we go along is that the needs traditionally, when we have one-way power flows, the needs of the bulk grid in terms of energy, the capacity, and the distribution system have been well aligned. As we go to this new paradigm where we try to decarbonize not both our buildings and our transportation, the three different areas start to diverge a little bit. And what we'll do is I'll focus a little bit more today on the distribution system because that's actually one that we don't talk about as much. But know that what we have to look at as we look forward is that we have to figure out how to get our buildings to actually connect together all these three different areas so that we can solve problems of all three different areas. So with that, can we go to the next slide, please?
And those three different areas, make sure I got them.
Yes.
Go ahead. Bulk grid energy, bulk grid capacity, and distribution system capacity. I don't think we'd forward those images. Okay. Sorry, continue on. Sorry, Ron.
Okay, no problem. So then you go to the next slide. We'll take a little bit of a walk down the woods into some of the projects and initiatives we have looked at in terms of building decarbonization. Next slide, please. This slide talks about a project that we completed a couple of years ago working with Southern California Edison, where we looked at what happens to the distribution grid when we start moving towards Z&E, right? So this work started in about 2013. 2020 was our Z&E goal. We worked with a production home builder. We said, okay, hey, how cost effective is it to go to Z&E? And then what we want to look at was the impact, and both in terms of flexible loads and what it takes in terms of distribution capacity. So we want to look at the impacts for Z&E communities. And what it turned out was that even about 5 years ago, we could get to Z&E new construction pretty easily. If you exclude the cost of the PV, the increase in home price was very, very minimal. And even with PV, it was less than 5%. And this is for a production home builder, right? You're asking them to change a few things. We went and electrified the end loads, the heating loads, the heat pumps, and the heat pump water heaters. And then we also wanted to look at, install connected loads for flexibility, batteries, connected heat pump water heaters, and connected thermostats, so that we could try to see how we can flex the loads. And if you go to the next slide, what we learned was that the combined cost of electric heating systems was only about $200 greater than going to a gas heating system. And the reason is that the cost savings come from not running the gas lines inside the house, but a big cost savings in going to electrification, new construction, was avoiding the venting. When you go to condensing tankless water heaters and high efficiency furnaces, the cost of avoided venting actually more than overcomes any additional cost for running 240 to the location where the water heater is. And then on the heat pump side, your cost increment is actually pretty minimal. What we found was that it was more a supply chain issue in that most of the product providers or the distributors were charging a few $1,000s more for heat pumps. I can get a heat pump from Alabama much cheaper than I can get it in California today, possibly due to installers not being familiar with heat pumps. So it's more a supply chain issue than an actual equipment cost issue. However, just recently we are working on some more communities now And in one of the communities, the plumber is now asking for $6,000 more to install a heat pump. It's a smaller builder. What we are still working with the plumber to see why they're charging that much and to educate the plumber. But what we do see consistently is that there is a pretty big gap in the supply chain for electrified heating system, for heat pump systems. In terms of actual data and results, what we found is that the actual energy use of heat pump water heaters was lower than what the models said they would be. But what we did see was a significantly higher operation of the electric resistance element compared to what the model said they would, which again impacts your overall efficiency for the heat pumps. And in terms of customer cost for new construction, as long as your envelope is really good, it's pretty much cost neutral. Again, I think it goes back to what Martha was talking about, that you have to get your envelope right before you go to electrification. Next slide, please. So this slide shows an analysis that we did recently. Martha had some really good slides too. And this analysis is to look at the carbon content or the carbon emissions from energy generation for a mixed fuel versus all electric homes. And what it shows is that even with today's generation mix, which is I think about 56% natural gas, and the rest of it, it's on the ISO, and the rest of it is carbon-free sources. We are still saving about 35% carbon going to a all-electric home. So one of the big successes that we are running, that we are working with right now, is we've been able to work with at least one top 10 home builder to build a completely all-electric community without any gas lines. And we're probably going to have a grand opening for that community in a couple of months. So we are able to work with the builders. When you sit down with them, you show how the economics work, but it takes a lot of work. Then you can actually work on electrification of new construction. Where we do run into some challenges is, of course, the cooking. And in the cooking area, I think it comes down to economics. If there is a valid economics in substantially reducing cost of running gas infrastructure, then the cooking can be electrified. Next slide, please. Where we do see a big challenge is, of course, in existing homes. Some of the work we have done in existing homes shows that it's pretty expensive. What it is that you have customer cost issue with the current rates, you have infrastructure issues, you have unavailability of products. So there's a whole multitude of different issues that we see. For example, with heat pump water heaters, what we find is that a lot of the existing products in the market don't fit into existing locations. You don't have 240-volt power in a lot of cases. Many homes, the panel capacity is not big enough for us to electrify heating systems. And of course, if you have to go to heat pumps and you have to put in backup electric resistance, then you probably don't have enough capacity. One silver lining is that we think that in areas where air conditioning is prevalent, switching over to heat pumps takes out a lot of the carbon content in existing homes, and that could be a low-hanging fruit to go after. Next slide, please. So this is just some examples of what we see consistently. So it goes back to the theme of infrastructure. A lot of the homes, we have existing panels that are 60 amp, 100 amp, 125 amp panels, especially in multifamily housing. And there is just not enough capacity for us to electrify the heating system. So we are actively working on looking for technologies that can help us avoid these upgrades of the existing systems. The challenge is that if you have to upgrade the panel, then you have to upgrade the conductor. You have to upgrade the panel at the overall building level if it's an apartment. Then if the panel goes up in size at the building level, now you have to replace the conductors on the distribution side, on the secondary side of the transformer. And if you do enough of that, now you have to upgrade the transformer. The costs just keep building up as you go step by step. Next slide, please. So what the next slide shows is an kind of an estimate of cost, right? In terms of making the changes from existing water heating to electrification of water heating. As you look at, one of the things that what we find is that taking existing electric water heaters, resistance water heaters, converting them to heat pump water heaters, actually has a greater carbon savings than trying to convert gas tankless to heat pump water heaters. So from a beachhead perspective, from getting the market going, from getting the plumbers and the installers going, that might be a great target to start with. And then, of course, at any point when you have to do a service upgrade or a grid upgrade, the costs just add up. Next slide, please.
Oh, Anne was wondering
Yes.
what you meant by the market split on this slide. There's the second column says market split. And it's like number 0.5. What does that mean?
So in terms of in that slide, it's an estimate of how much we think we can actually turn over. So when we say the market split, it is about the availability of 240 at the location of the water heater to be able to convert from fossil fuel over to electric. So for example, what we estimate is that, hey, for where houses are running on propane, there's probably a little bit more capacity available because houses, you don't have natural gas, whereas many of the houses that might be running on natural gas, you might be really constrained on capacity, which means that we estimate, that's just an estimate of, we think that 80% of homes with natural gas are going to have trouble with conversion of water heaters.
Thank you. Yep.
If you go to the next slide, this is what we call the cost stack in building retrofits, which is the equipment cost is just the tip of the needle. If you just have to replace equipment, it's pretty cheap. If you have to upgrade the panel in the building, it's expensive, but not too bad. Once you start adding additional, like running additional 240 wiring, and then if at some point you just don't have enough distribution system capacity, that's when the cost really starts adding up. I think the estimate is that if you really have to upgrade distribution, you're looking at about $20,000, $25,000 per home for a full electrification retrofit. So if you're going after decarbonization, I think what we really have to look at is the overall system cost and try to understand where the low-hanging fruit might be for decarbonization. Next slide, please. So just going through the experiences around electrification of existing buildings and new construction, that leads us to, okay, hey, we realize that the big wild card here, and the EVs have already gone through that cycle, right? That's why we have huge $750 million program for EV charging infrastructure, right? Because they have the same issues. Now, what we're doing is the building side is actually following the EV side maybe 10 years behind, but we are running into the same issues with the grid edge, what we call the grid edge distribution system. Next slide, please. So one of the first things is when you think about distribution systems, there's two things. There's operations and there's planning. When we talk about controls, usually we talk about operations. And operations is for existing distribution systems that are already there. When you are actually trying to understand what you have to do on the hardware, which is the transformer size, the conductor size, you're in this planning mode. And planning usually is a function of the connected load. It's not a function of the controls or how the flows work on a real-time basis. And the reason is this, it's pretty simple. If at some point your battery controls, today we can actually change your battery controls over the air almost instantaneously. If your battery control suddenly suddenly stops working and it flips the battery from delivering energy back to the grid versus actually pulling energy, right? Suddenly you're splitting from being a generator to a load, which means that when you're doing planning, you're planning a 50-year asset, and you cannot depend on things like over-the-air control algorithms to actually plan a 50-year asset. So when we plan these assets, it's always planned as a plan based on how much load is connected. So if you look at traditional load calcs, especially in California, our biggest loads being in most homes has been air conditioning. Yes, some homes have electric cooktops, especially multifamily. That's a pretty big load. But other than that, it's been either air conditioning or cooking, and then lights and plug loads and appliances. So traditionally, we have designed around about 6 to 7 to 8, maybe kilowatts per home of connected load. You have some load diversity. There's a calculation procedure according to the National Electric Code. When we go to what I call the decarbonization era, right now your connected loads are substantially higher, even if you use a lower load diversity number, which is kind of going back to the fact that your loads are now a lot more variable. You are still looking at a much higher connected load. So as we add EVs, as we add batteries, as we electrify heat pumps and heat pump water heaters, we are going to start running into this problem more and more because our grid really is, it needs to be updated for decarbonization. So if you go to the next slide, please. This shows you what happens, right? You saw that first, the one on the graph on the right in the first slide, where you look at the net load from a home, and it's just all over the place. It's highly variable, there's needle peaks. And what we find is that you don't have that nice clean load shape anymore. You have a whole bunch of needle peaks. And especially when you electrify heating systems, you have a higher probability of your heat pump water heater and your electric heat pump running at the same time. And then those seem to be peaking, let's say 8 p.m., 9 p.m., that's when people come back and all the loads are starting up. If you plug in your EV at the same time, now suddenly you have some huge load peaks that you have to address. And so that's the discussion that we have to have, which is moving forward. How are we going to adapt our distribution system so that we can actually electrify and decarbonize our building stock? Next slide, please.
Ram, 5-minute warning.
Yes.
I wanted to interject that there's also the possibility of limiting the power requirements of equipment versus upgrading the grid. I mean, that's at least maybe part of the solution, is going to the equipment and saying you just can't use 30 amps. If you're a water heater, you can only use 5 or 10. How does that enter your thinking? Like what we can do?
Absolutely. I think that's part of the solution here too. So we have to look at it both ways. And again, that's the product gap I think I referred to in an earlier slide. So Sean, given that we have 4 minutes, let me try to quickly run through, and then maybe we'll have a couple of minutes for questions. But you're absolutely right. That's the other thing that we have to work on. So I'll skip through. If you go to the next slide, the next 2 or 3 slides just talk about, hey, what happens on the distribution planning side. We actually ran some analysis on distribution system sizing, and it shows that if you go to the slide with the two sets of graphs, right? What it shows is that if you operate your battery based on TOU rates, it actually makes the feeder worse. It really increases the loading on the feeder, versus if you operate the battery to soak up excess energy, that is run it in self-consumption mode. But what happens is that today, most of the batteries, especially on the residential side, are designed to run on TOU, right? And so when you run it on TOU, it's essentially running wild. A lot of times it's the charging peaks might actually coincide with your load peaks, which means that you might really end up stressing the distribution system a lot more versus running it in self-consumption mode. So part of it is we really have to think about, as we start deploying more batteries, how do we charge these batteries? What is the optimal way of running these batteries? Next slide, please. So one more slide. So part of this is that when we talk about storage, as we look at the evolution of the grid, there are multiple forms of storage. There's batteries, but there's also water heaters, there's ice storage, there's storage in high mass walls. And we have to look at all those types of storage too in the future evolution of the grid. Next slide, please. So part of, I think, where we need to look at from a building's perspective is how are we going to make buildings and building controls work in a coherent manner between different types of energy storage so that we can do balancing at the distribution system level, at the local level, right? If you're able to charge more, what do you actually charge? Do you charge your building envelope? Do you charge your water heater? Do you charge your batteries? When do you charge each of these? And how do you actually balance all these out? How do you control all of them? I think it's going to play a key role as we move towards the future of the grid, as we try to transform the grid. Next slide, please. This is a example of using water heaters as storage. One of the things we noticed with heat pump water heaters, of course, is that if they run correctly, the capacity response of heat pump water heaters is only about 200 to 400 watts. So at aggregate, we might still get some decent capacity, but individually, they're all pretty small. And that's the way we want it to be. If your heat pump water heaters run efficiently, and Sean, to your point, if we reduce the power draw of those, they just don't have that much capacity or capability to move load, right? But that's a good thing. That's what we want with electrification. Next slide, please. Same thing with smart thermostats, right? If you run smart thermostats, if you do pre-cooling, what we find is that they have some significant storage capacity. And in aggregate, they can be used to manage, modulate, and balance the distribution systems, as well as provide services back to the ISO. Last slide, next one. So what do we see as the future, right? The future is that, hey, we have to look at distribution planning. How are we going to do our distribution planning differently for electrification, decarbonization? But then we also want to look at, as we get more connected loads, whether it's EVs, whether it's commercial buildings, whether it's residential buildings, how are we going to get these controls so that we can do better aggregation and better what we call orchestration, which is you provide customer benefit through orchestration so that you reduce your customer cost through time of use rates, and then do the aggregation so that you can provide not just services back to the ISO, but also services back to the distribution side of the grid, which is where I think the action is going to shift as we go to the future where it's more deep, where we drive decarbonization, where we drive greater penetration of electrification of end users. So with that, I will stop, and if there's any time for questions, we'll take questions. Or
hey, Ram. Well, we're at the 3:30 point. So you know, if you over in the comments, you know, people are commenting how equipment can be operated to meet time of use needs, which I know you know, and I was interested in your thoughts on the role of EV sharing with daytime charging to solve needle peaks. So she's interested, like using cars for offsetting needle peaks. Any thoughts?
Yeah, no, I think that's a great thought, right? I mean, that's kind of where we need to go. I think the real value for electrical storage is going to be actually addressing those needle peaks. It's not the bulk load shifting, but the needle peaks. If we can show that we can consistently hit needle peaks, it could essentially help us a lot with the distribution grid of the future.
Okay then. So I know that some of your needle peaks were because of electric resistance elements kicking in on water heaters. I wanted to see when your slides.
Yes.
And so yeah, I'm really excited about banning some of the needle peaks like that. But can't ban a cook stove, and that's just as much. Or ban a dryer for that matter.
It's interesting times. A lot of things that for us to look at, right? There's a huge palette of technologies and devices for us to look at as we move to the future.
Well, thank you for explaining the big picture, bringing your insight from your global travels to us. Thank you, Ram. Yay, Ram! Yay!